What is dark matter? Opening hook. The unseen universe. Greetings, cosmic explorers, and welcome back to Cosmic Enigma, where we unravel the universe's deepest secrets. Today, we're tackling a question that will fundamentally change how you see reality. What is dark matter? When you gaze up at the night sky, you see countless shimmering stars, beautiful nebulae, and majestic galaxies. But what if I told you that everything you can observe, every planet, every star, every galaxy, and even ourselves, accounts for a mere 5% of the universe's total composition? That's right, a staggering 95% of our cosmos remains shrouded in mystery, hidden from our direct view. This immense scale of the unobserved compels us to ask, what else is out there, quietly orchestrating the cosmic dance? The invisible majority, defining dark matter. At the heart of this cosmic enigma lies dark matter, a substance unlike anything we have ever directly encountered. It's called dark, not because it's merely obscured or hidden, like a black hole or a cloud of cold gas. No, it's dark because it fundamentally does not interact with light or any other form of electromagnetic radiation. This means it neither absorbs, reflects, nor emits light, rendering it utterly invisible to our telescopes and instruments. Its presence is inferred solely through the powerful gravitational effects it exerts on visible matter. To truly grasp dark matter's significance, consider the universe's full inventory. Approximately 5% is normal or visible matter. A substantial 27% is dark matter, and the remaining 68% is an even more mysterious force known as dark energy. This cosmic census highlights dark matter's profound dominance, making it roughly 5 times more abundant than all the ordinary matter combined. It is crucial to understand that dark matter is not a force like gravity, but rather a substance, likely composed of tiny particles, much like air is made of molecules, albeit particles vastly different from those we know. This fundamental distinction in its nature, its lack of electromagnetic interaction, is precisely why it has remained so elusive and why it demands new physics beyond our current standard model of particles. Unseen hand, visible effects, the evidence for dark matter. How do we know something invisible is out there? The story begins in the early 20th century with astronomer Fritz Zwicky. He noticed galaxies within clusters were moving at speeds far exceeding what the observable mass could account for. They should have torn themselves apart. This cosmic discrepancy suggested the presence of unseen mass. Decades later, in the 1970s, pioneering American astronomer Vera Rubin provided compelling evidence through her studies of galaxy rotation curves. She observed that stars at the outer edges of galaxies orbited just as quickly as those closer to the galactic center, rather than slowing down as expected. This flat rotation curve indicated that galaxies must be embedded within vast invisible halos of dark matter, extending far beyond their visible boundaries and providing the extra gravitational pull needed to keep them cohesive. Further evidence accumulated through gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Massive objects, including concentrations of dark matter, warp the fabric of space-time, bending and distorting the light from more distant background galaxies. By analyzing these distortions, astronomers can map the distribution of unseen mass, revealing vast reservoirs of dark matter where little visible matter exists. Perhaps the most striking visual proof comes from the Bullet Cluster, a pair of colliding galaxy clusters. Observations by the Hubble Space Telescope and Chandra X-ray Observatory showed that during this titanic collision, the ordinary matter, hot gas, which emits X-rays, interacted and slowed down, while the dark matter passed right through, largely unaffected, clearly separating from the visible components. This distinct separation provides powerful, direct evidence that dark matter behaves differently from normal matter. Finally, observations of the cosmic microwave background, CMB, the faint afterglow radiation from the Big Bang, offer crucial insights into the early universe. Fluctuations in the CMB provide a snapshot of the infant cosmos, and their patterns are consistent with a universe where dark matter comprised about 27% of its total contents, playing a vital role in the formation of cosmic structures from the very beginning. The convergence of these multiple, independent lines of evidence, from galactic scales to cluster dynamics and the echoes of the Big Bang, paints a consistent and robust picture, strongly affirming the existence of dark matter, even if its true identity remains a mystery. The quest for identity. What could dark matter be? While the evidence for dark matter's existence is overwhelming, its fundamental composition remains one of science's greatest unsolved puzzles. Scientists hypothesize that it is made of new exotic particles not accounted for in a standard model of particle physics, which describes all known fundamental particles and forces. One of the leading candidates for decades has been the weakly interacting massive particle, or WIMP. As the name suggests, WIMPs are theorized to be massive particles that interact only very weakly with normal matter, primarily through gravity and possibly the weak nuclear force. Their theoretical appeal was bolstered by the WIMP miracle, an intriguing coincidence where many supersymmetric extensions to the standard model naturally predict a stable particle with precisely the properties needed to explain dark matter's observed abundance in the universe. However, the scientific landscape is dynamic. Despite extensive searches, definitive direct detection of WIMPs has remained elusive, and the Large Hadron Collider has not yet found evidence for the supersymmetry theories that predicted them. This lack of confirmation has led researchers to explore other promising avenues. Enter the axion, another compelling candidate gaining significant attention. Axions are characterized by their extremely low mass, far lighter than WIMPs, and even weaker interactions. Recent research suggests that axions could be a more viable candidate, potentially explaining observed gravitational effects without contradicting existing particle physics models and having been produced in sufficient quantities in the early universe. Beyond WIMPs and axions, other theoretical possibilities include particles from a hidden valley, a parallel world made of dark matter, or other exotic particles that form a dark sector with very little in common with the matter we know. This evolving landscape of candidates demonstrates how experimental results continuously refine our theoretical understanding, pushing the boundaries of discovery. Hunting the ghost particle. Experimental detection methods. The elusive nature of dark matter, stemming from its incredibly weak interaction with ordinary matter, makes its direct detection an immense scientific challenge. It's akin to trying to catch a ghost. We see its effects, but it slips through our grasp. Nevertheless, scientists employ a multi-pronged approach in their quest to unveil its identity. One primary method involves direct detection experiments. These sophisticated setups are often located deep underground, shielded from cosmic rays and other background noise, to create an ultra-quiet environment. Here, highly sensitive detectors, typically made of materials like xenon or germanium, are designed to register the minuscule recoil that would occur if a dark matter particle were to directly collide with an atomic nucleus within the target material. Experiments like Xenon 1T and CDMS are at the forefront of this challenging search. Another approach is indirect detection. If dark matter particles can annihilate or decay, they might produce detectable particles, such as gamma rays, neutrinos, or positrons. Astronomers use powerful telescopes on Earth and in space, like the Fermi Gamma Ray Space Telescope and the IceCube Neutrino Observatory, to search for these telltale signatures emanating from regions where dark matter is expected to be abundant, such as the galactic center or dwarf galaxies. Finally, collider experiments, such as the Large Hadron Collider (LHC) at CERN, also play a role. While they cannot directly see dark matter particles, if these particles are light enough to be produced in high-energy collisions, they would escape the detectors unnoticed. However, physicists could infer their existence by observing a missing amount of energy and momentum after a collision, indicating that something unseen carried it away. The persistent lack of definitive detection across these diverse and increasingly sensitive experiments is not a failure, but rather a crucial step in scientific progress. It continuously narrows down the possibilities for dark matter's properties, suggesting it might be even more weakly interacting or have different characteristics than initially theorized, pushing the boundaries of our understanding. Cosmic architect, dark matter's role in the universe. Beyond its mysterious nature, dark matter plays an absolutely fundamental role in shaping the cosmos as we know it. It is not merely an additional component. It is the invisible architect, the gravitational scaffold upon which the entire visible universe is built. Without dark matter, the universe would look profoundly different. Its gravitational pull acted as the crucial seeds in the early universe, attracting normal matter, gas and dust, to clump together and form the first stars and galaxies. Today, dark matter halos, vast spherical distributions of this unseen substance, envelop galaxies, providing the necessary gravitational glue to prevent them from flying apart as they rotate at incredible speeds. Similarly, the immense gravity of dark matter holds together massive galaxy clusters, which would otherwise disperse due to the high velocities of their constituent galaxies. On the grandest scales, dark matter forms an intricate web-like structure that winds through the entire universe, known as the cosmic web. This gravitational framework consists of vast filaments and sheets of dark matter, with galaxies and galaxy clusters congregating at the densest intersections, akin to pearls on an invisible string. This cosmic blueprint, dictated by dark matter's gravitational influence, is essential for understanding the large-scale distribution of matter in the universe, and how cosmic structures evolved over billions of years. Its profound influence underscores that dark matter is not just a missing piece of the puzzle, but a foundational element dictating the universe's past, present, and future structure. Dispelling shadows, dark matter versus dark energy and misconceptions. It is a common source of confusion, but despite their similar names, dark matter and dark energy are two entirely distinct cosmic mysteries with fundamentally different roles. This semantic trap often leads to misunderstanding, so it is vital to clarify their unique properties. Dark matter is a mysterious substance that exerts a gravitational attraction. It clumps together, forming halos around galaxies and providing the gravitational scaffold that allows large-scale structures like galaxies and galaxy clusters to form and hold together. It makes up about 27% of the universe's mass energy content. Dark energy, by contrast, is a mysterious force or property of space that creates a repulsive gravitational effect. It is distributed evenly throughout the universe and is responsible for the accelerating expansion of the cosmos, pushing galaxies further apart instead of pulling them together. Dark energy is believed to constitute an astonishing 68% of the universe's total mass energy density. They are quite simply cosmic opposites in their effects. Beyond this crucial distinction, several other misconceptions about dark matter persist. It is not simply dark, normal matter like black holes or cold gas. Its darkness signifies a lack of electromagnetic interaction, implying a completely new type of particle. Furthermore, dark matter is not a force in itself, but a substance made of particles that exert gravitational force. And finally, despite the compelling indirect evidence, dark matter has not been directly observed yet. All our current knowledge comes from its gravitational imprint on the visible universe. Clarifying these points is essential for a precise understanding of these profound cosmic components. Concluding thoughts: the ongoing cosmic enigma. Dark matter remains one of the most profound and persistent mysteries in modern science. Its existence is overwhelmingly supported by a convergence of independent observational evidence, from the rotation of galaxies to the collision of galaxy clusters and the very echoes of the Big Bang. Yet, its true identity, the fundamental particles that compose it, continues to elude us. The quest to unlock its secrets is a global scientific endeavor, pushing the boundaries of particle physics and astrophysics. Future missions like NASA's Roman Space Telescope and ESA's Euclid mission are specifically designed to map its distribution with unprecedented precision and search for new clues. Unraveling the nature of dark matter will not only complete our cosmic inventory, but will also revolutionize our understanding of the universe's fundamental laws, its origins, and its ultimate fate. The universe in its vastness still holds many secrets, and dark matter stands as a testament to the endless frontiers of discovery. Stay curious, cosmic explorers, for the greatest revelations may still lie unseen.